All right, so I'm going to be switching gears, and no matter how good the simulations were before, they're not going to find planets. But I am going to be talking about the very small scales and planets and how we find them, and how our group at the University of Washington has sort of done the best job with making do with what we can. So just to real quick outline, I'm going to be talking at first to sort of introduce how we find planets to those who may not be astronomers, and then get into what exactly Kepler and K2 is and what they've been doing, and how I use them to find planets. And then we'll talk a little bit about the results and what is coming up next. And there's a very big thing coming up next that I'll get to. So there's lots of different ways to find planets, but we are focusing on the transit method, which uses the fact that if planetary systems happen to be perfectly aligned, when we look at them from Earth, you will see planets pass between us and the star, and those planets will sort of cast a shadow and block some of the light from the star. And depending on how big the planet is, that tells you how much light is blocked. And so if you see these dips, you can tell how big the planet is, and how often these dips occur tell you how far away the star or the planet is from its star. And so like Jupiter, for instance, blocks about 1% of the sun's light, whereas Earth is much smaller and blocks a hundredth of that. The problem with the transit method is, like I said, it has to be perfectly aligned. So you can only see this if the planetary systems are pointing sort of right at us, which means that you have to get lucky. So only about 1 in 200 stars would see the Earth transit, for example. So to do this, you need to beat the odds, you need to look at lots and lots of stars. And so that's what Kepler, the telescope, was designed to do. It was launched in 2009, and it had a 1.4 meter mirror, not too big for a telescope. And at the time, had the largest camera ever launched into space at 96 megapixels, and a very, very massive instrument, as you can see with the person to scale there helping to build it. And so Kepler, its job was just to look at 250,000 stars, the same stars over and over for 4 years, and just measure their brightness every 30 minutes, and wait for these dips in brightness to occur that indicate that a planet is there that is transiting. And so this is just a picture of the field of view, and it's a relatively small piece of the sky. So the Kepler, this square, is kind of sort of the size of your hand held out at arm's length on the sky. Not a very large picture of the sky, but as you can see on the right, well, there's lots and lots of stars in there. There's plenty for Kepler to look at. And so it picked 250,000 stars in this image to look at for every 4 years and find these transits. And it worked. So this is a picture of where the state of transiting planets was in 2009 when Kepler launched. And there were a smattering of them, but most of them were Jupiter-sized. And there's just not that many on there. If we move ahead, there we go. So that's after 2 years of Kepler data, half of the Kepler data, and you can see that it just revolutionized the field of transiting planets and added hundreds more. And then we skip ahead 2 more years of data, and this is sort of the final sample from Kepler. And all those yellow points are the Kepler planets that just outnumber everything else we've found. And in fact, Kepler has found roughly 2/3 of all exoplanets of any variety that we know about today. And the most interesting part is that, as you can tell, this yellow cloud is distinct in that it is the size of Earth and Neptune. So most of the planets that Kepler is finding are the size of about Earth and Neptune, as opposed to all the other methods that still are mostly just finding Jupiters, which are interesting, but we are most interested in sort of rocky Earth-type planets. So Kepler was launched with about 10 years of fuel, so it was planned to last until about 2019, 2018, which is about now. But I've been saying only 4 years of data. And that's all we had. So what happened in 2013? So it was my end of my first year of grad school. I was planning to do my entire thesis on Kepler. And then the news started rolling in that got picked up by lots and lots of networks that was basically saying Kepler's done for, something broke. this mission is coming to an end, what's going on? And what happened was that Kepler lost the ability to point in all three directions. So if you're using a telescope to point very precisely at stars, you need to keep the telescope oriented in all three dimensions. And it lost its ability to point in one of those dimensions. And the effect of that is that photon pressure from the sun hitting the solar panels was enough to sort of, over time, add up a force large enough to sort of send the spacecraft into a barrel roll. And without the ability to finally point in all three dimensions, it can't correct that very easily. And so that basically ended the Kepler mission. It could no longer finally point at stars. But the engineers didn't quite give up, and they realized that if you happen to orient the spacecraft just right so that it is the solar pressure from the photon pressure from the sun is perfectly balanced, then you can get a much more stable spacecraft and still do some science. It's not perfect, but you can get back to doing some science. And so that's what K2 is this new mission, because you sort of no longer have a choice of what stars you're looking at. You just sort of take the spacecraft and balance it against the photon pressure, and whatever it's looking at, those are the stars you collect. And the problem with that is that every 90 days, the spacecraft goes a quarter of the way around the sun. And that means A, your photon pressure is all messed up again, and B, the sun is starting to actually get in the way of the telescope. And so you can no longer look at stars, you're just blowing out your telescope looking at the sun. So K2 instead, just every 90 days now, it's just been turning itself around, rebalancing against the photon pressure, taking more data against just new stars. And it's been doing this for the last 5 years. And so this is just sort of, it's just tracing its path across the sky. Whatever stars happen to get in its way, it's taking data for. The problem is, as I mentioned, it still can't finally point. And so even though it's more stable, it's not perfectly stable. And to demonstrate that, here are some GIFs. On the left is a GIF, even though it looks like a still image of original Kepler data, and that just shows how precisely the telescope was pointed, where it got the same light from the star on the same parts of the pixels all the time. And on the right is K2, and it's still keeping the star roughly in the same spot, but it's no longer perfectly oriented. And this extra noise is enough to cause about a factor of 4 decrease in quality in your light curves, which makes it a lot harder to find planets, especially when you only have 90 days of data to look instead of 4 years. And so this was enough for the official Kepler team to say that their planet search that had found all those 4,000 planets in the original Kepler mission, their planet search can't handle K2. It's done. They will keep taking the data, but finding planets is left to the community. And so that opens things up for a whole bunch of different groups to try to jump into this raw data, fix it, and find planets. And so that's what our group at the University of Washington has been doing. So I'm going to talk just really quickly about sort of how this works. It's a brief overview. If you want to talk to me more about it, I have a poster up tonight, or you can find me all week. But we have this pipeline. We call it EVEREST that fixes K2. And so on the top is the raw K2 data, and you can see all those like jittery lines that is caused from the spacecraft jumping around all over the place. And on the bottom is what we've done after we run EVEREST, and EVEREST essentially is able to just say, it's able to pick out which bits of noise are caused from instrumental effects and model that, and then remove it. And so all you're left with is just the noise from the star. Then you're left with just pure stellar light. And so on the bottom there is what we have after we run EVEREST, and all those points below sort of the main line there are transits. Those are planets you can just pick out by eye. So we've fixed the K2 data quality and brought it back to Kepler quality, and now we can use it to find planets. So that's what I've been working on. Is I am in charge of designing the planet search, and I've been working on that for a couple years now. So the thing about finding planets, searching for planets with transits, is more or less, no matter which, there's a bunch of different methods, but they're all basically the same. And how it works is you effectively have to search over a 4-dimensional grid of all the different potential combinations of planets that might be there, and you compare them all and see which one fits the data best, or if any of them do. And so what we do is we have a grid of 10 different transit depths, 16 different durations of how long the transit might last, and then you have to look at all the different possible periods and phases that this planet could exist at. So from down to like 0.2 days, rapidly circling around the star, all the way out to just a single transit happening once. And we have to search all these different grid points, and that is where the computational challenge comes in, and that's where Blue Waters helps. Sorry. All right, there we go. So that's where Blue Waters comes in. And so I've got this 4-dimensional grid of planets or potential planets to be looking for. So it ends up being about 1 million different grid points per star, which takes about 30 minutes on a single CPU. And Kepler, their K2 at least, so far has returned data for 500,000 stars. And so this is a lot of CPU cycles just to search things once. And so that's what I've been sort of using Blue Waters for. We've only gone through the first half of the K2 data so far. We still have another 200-ish thousand stars left to search. We're hoping to speed up the process and get things moving more quickly. But for now, I'm going to show you our results from the first half of K2, the first couple 100,000 stars. And so our Everest pipeline and our planet search is working just great. So I'm going to show you the Kepler sample again, except these are going to be black points. And then I'm going to show you my planets on top, K2, different set of stars. But these are the blue points, is our planet candidates, our 700 planet candidates. And as you can see, they're basically the same. It's the same distribution. And so that shows us that our search is working right. We're weeding out false positives correctly. We're drawing from the same distribution of planets that Kepler was finding, except that ours is cut off at about 40 or 50 days, whereas the Kepler sample goes out to hundreds of days. And that's just because, as I said, we are only looking at 90 days at a time of data, whereas Kepler had the full 4 years. But we have 700 some odd planets right now. Ours is the most successful search of K2. Other groups, as I mentioned, have tried this. And altogether, they've found about 300 of them in various combinations. But we seem to be the most effective group. And we're reproducing original planet samples. And we have some really interesting dynamical stuff going on in some of these. So one of the maybe surprises of Kepler was that there's a lot of short period planets, and they seem to be dynamically interesting. Whereas in our own solar system, the planet periods are spaced out, but not really perfectly in any interesting combinations. In these short period planet systems, there's this preference for the periods of the planets to be in almost exact ratios. So for this instance, this 3:2 line, this massive peak there, granted it's small sample sizes, so massive peak means 9 systems. But still, it's above the background. That 3:2 ratio means that for every 3 times an inner planet goes around, the outer planet will go around exactly twice. And they seem stuck at almost exactly this ratio of 1.5 period ratios. And that seems to tell us something about their formation or their evolution, where these planets might migrate inwards and get sort of trapped near these resonances and sort of stay there forever. And there's lots and lots of other interesting results that we have, but I'm going to cut things a little bit short and just invite you to come talk to me at my poster or anywhere else this week. But real quickly, I just want to talk about what's coming up next and why things like Blue Waters are going to be even more important. So up next is something called TESS. And so like I said, K2 had enough fuel, or Kepler had enough fuel to last until about 2018, 2019. And it has continued to work even though K2 is not exactly what they wanted to be doing with it. We've made the best of it. But fuel is running out. And those of us who keep up with K2 and are working with the data basically check Twitter every day to see if the spacecraft is still functioning. We're expecting the fuel to run out any day now. But we've planned ahead, and TESS is the next Planet Hunter. And it is essentially a spacecraft with 4 telescopes in one. If you can see that on that slide. It has 4 different imagers all bundled together into this one spacecraft that launched a couple months ago. And it is going to be surveying the entire sky, not just the size of your hand. And so I want to just demonstrate that with this movie. So here's the original Kepler field. And we're going to show you one TESS camera is even bigger than the Kepler field. And then zooming out and showing you all 4 TESS cameras piled up here. And then let's compare that to everything K2 has done over its 5 years of operation. Those are all the K2 fields. So those are the entire piece of the sky that we've searched so far. And there TESS goes. And that's what it's going to be doing. So TESS is going to be tiling the entire sky, basically searching every single star out there, at least the brighter ones for planets. And so instead of K2, one of those little yellow dots is what we had 90 days of data for to search, is going to turn into 3 of those stripes from TESS in the same amount of time. And so all of the planet hunters are gearing up for a massive amount of data to be searching through. It's going to be a fun game, fun few years with TESS as we find hundreds or thousands of new planets around the brightest stars, the closest stars pretty much anywhere in the galaxy. So it's going to be really exciting, and we're going to need all the computers we can get to do this stuff like this. So just to conclude, our group at the University of Washington has sort of developed the best way to turn K2 data back into Kepler data, use it to find planets. We found hundreds of planets so far in only the first half of K2. And we have thousands more stars to go, and we're just gearing up. We're sort of in the prologue right now as TESS is going to change everything we know about planets all over again. So thank you.